Here is a presentation of the Python wrapper for hyperparameter optimization benchmarks using parallel setups. First, I would like to introduce hyperparameter optimization. Hyperparameters are very important for the performance of machine learning. Here is a figure to show the relation between hyperparameters and model performance. The x-axis and y-axis show hyperparameter values, and the color shows the performance of a model. In this figure, good performance is colored red, and bad performance is colored blue. As can be seen, the performance highly depends on hyperparameter settings, and this is why hyperparameter optimization is essential. In order to push the research in hyperparameter optimization, many benchmark datasets have been invented so far, but they primarily focus on non-parallel optimization setups, and it's hard to be benefited from the benchmarks in terms of runtime reduction. For this reason, we developed a Python wrapper to address this problem and present the wrapper in this presentation. Here are the contents of this presentation. First, I will present the workflow of hyperparameter optimization. In the visualization, the horizontal axis shows runtime of hyperparameter optimization. We first sample hyperparameter configuration. Then, we wait until the evaluation finishes and return the result to the optimizer. After collecting the result, we sample another hyperparameter configuration. The optimizer takes its result, the optimizer samples, takes its result, samples, then the optimizer waits till the end of the final evaluation. Many hyperparameter optimization benchmarks use a tabular format or surrogate model. A tabular benchmark contains pre-recorded results for all possible configurations in a given search space. A surrogate benchmark uses a machine learning model trained on collected observations in a given search space. When using a tabular or surrogate benchmark, the variations of each hyperparameter configuration can be queried in a fraction. In the example of the presentation as well, we can shorten the runtime for each query. Then, the actual runtime will look like this. Next, we show how you do the same for parallel optimization. We use the same visualization as before, and W1, W2, and W3 stand for worker 1, worker 2, and worker 3. We first sample hyperparameter configurations for each worker. Then we wait until one evaluation finishes and return its result to the optimizer. After collecting the result, we sample another hyperparameter configuration for the finished worker. The optimizer waits until the next end of an evaluation and takes the result. The optimizer samples, waits until the next end and takes the result, samples, waits until the next end and takes the result, samples, waits until the next end and takes the result. We repeat it until the budget runs out. The question is, how do we compress runtime in this case? The challenging part of the compression came from the fact that each worker needs communication. However, as long as we can keep the same order of returning each result, we can obtain the same result with a much shorter runtime. Finally, we show how our wrapper works. The first challenging part is communication between workers. The second issue is that the mechanism of optimizers takes diverse formats, such as multi-processing, multi-threading, and MPI. To handle these issues, we use file system to let each worker communicate. We first sample hyperparameter configurations for each worker. Then we report the runtimes for each sample to the file system. Then our wrapper checks the minimum total runtime and terminates the sleep for this worker. And the worker returns the result to the optimizer. Then the optimizer samples for the freed worker. The wrapper reports the runtime, updates the total runtime, checks the minimum total runtime, finishes the sleep for this worker, and returns the result to the optimizer. Samples, reports the runtime, updates the total runtime, checks the minimum total runtime, terminates the sweep for this worker, and returns the result to the optimizer. Samples, reports the runtime, updates the total runtime, checks the minimum total runtime, terminates the sweep for this worker, and returns the results to the optimizer. Samples, reports the runtime, updates the total runtime, checks the minimum total runtime, terminates the sweep for this worker, and returns the result to the optimizer. Samples, reports the runtime, updates the total runtime, checks the minimum total runtime, terminates the sweep for this worker, and returns the result to the optimizer. We repeat the routine until the specified budget runs out. Finally, I present the wrapper usage and its performance on a synthetic function. Here is a code block example. The first code block does not use the wrapper, and the second code block uses the wrapper. The differences lie only in highlighted lines. When we do not use the wrapper, the objective function needs to sleep, but no need to sleep when we use the wrapper. Instead, the objective function needs to be wrapped by our wrapper. We have many examples on GitHub, so please check out our repository for more details. Now, I show the performance benchmark of a naive implementation and our wrapper. The x-axis is the wall clock time, and the y-axis is the performance, which is better when it's lower. The first point is the two lines at the right part of the figure. Although it's hard to see, these two lines completely coincide, and it means that our wrapper perfectly reproduces the same result as the naive implementation. Furthermore, the left part shows that our wrapper significantly reduces the runtime and finishes the optimization in a second while maintaining the simulation result. This example uses a function that costs at the most 10 seconds, but if the function cost is more expensive, the time-saving effect becomes more significant. Here is the conclusion of this presentation. In this presentation, I introduced a Python wrapper for parallel optimization and demonstrated the wrapper significantly reduces the runtime of experiments. This is the end of the presentation. Thanks for listening.